Hello, this is the second video of a second-order differential equations third series on modelling with second-order differential equations for OCR Pure Core Further Mathematics, and it looks at damped oscillations. In the last video, we looked at simple harmonic motion modelled by the equations of form d2x by dt squared equal to minus omega squared x, which had a general solution of x equals a sine omega t plus epsilon. This potentially has constant amplitude and periodic motion which goes on forever. However, we should note that in the real world the motion would slow down with the amplitude reducing due to factors such as air resistance or friction. So, whilst the equation is a good model for some situations, there are many others where the amplitude of the oscillations decreases with time, and this is called damped oscillations. The equation d2x by dt squared equals minus k dx by dt minus omega squared x adds in a resistive element proportional to the first derivative, which in effect factors in the motion slowing down. If we consider the auxiliary equation method using lambda, we would get an auxiliary equation lambda squared plus 2 lambda plus 10 equals 0 for this example here. If we complete the square, we would get lambda plus 1 squared plus 9 equal to 0, and then lambda equal to minus 1 plus or minus 3i as the two complex roots. Note that in this situation we have the form alpha plus beta I, where alpha equal to minus 1 and beta equal to 3. We've looked at complex roots or auxiliary equations in the previous video series, so therefore we know that we can use the standard result for this situation. Therefore, the general solution will be x equals e to the minus t p cos 3t plus q sine 3t. We can go on to find a particular solution if we are given some additional information. In this example here, we are told that x equals 0 and dx by dt equals 1 when t equals 0, in other words, some initial conditions. We know what our general solution is. Consider then t equals 0, and substituting in, we know then that 0 will equal e to the 0 is 1, cos of 0 is 1, so just giving us p, and sine of 0 is 0. Therefore, we just get the result that p equals 0. Considering then dx by dt, we know that p is 0, so we're just going to differentiate the e to the minus t q sine 3t, and that would give us minus q e to the minus t sine 3t plus 3 q e to the minus t cos 3t. Putting this equal to 1 when t equals 0 will give us just 3q. Thus q equals a third. And we can write the particular solution as being x equals a third e to the minus t sine 3t. Here is the graph of that particular solution. Note that at t equals 0, x equals 0, and that the gradient dx by dt equals 1 at that point. The solution oscillates as with simple harmonic motion, but notice that the amplitude is decaying, and it lies between the curves, or the envelope of the curves, x equals plus or minus a third e to the minus t. The period of the oscillation, as expected, given that omega equals 3, is 2 pi over 3. In the next video, we look further at damped oscillations in terms of plotting and interpreting the solutions.